Hey everyone, and welcome. Today, we're going to tackle a super common puzzle in data. How do you compare a bunch of different options at the same time without messing things up? We're going to break down a really powerful tool called ANOVA that's built to do exactly that. Comparing just two things is pretty easy, right? It's a simple A-B test. But what happens when things get more complicated? What if you're a marketer with, say, 3 different ad campaigns? Or a doctor trying to compare 4 new treatments? As we're about to see, just trying to compare them 2 by 2 can get you into some real statistical trouble. So what's the big deal? What's the trap we're trying to avoid here? Let's take a look at the most common, but also the most flawed way people try to handle this. Okay, so let's say you've got 3 new drug treatments. The obvious thing to do, your first instinct, would be to just compare them 2 at a time, right? You'd run a test for drug A versus drug B, then another one for A versus C, and then a final one for B versus C. Makes sense on the surface. But, here's the catch. Every single one of those tests has a small chance of being wrong, of giving you a false positive. Statisticians call this a type 1 error. It's kind of like playing the lottery. The more tickets you buy, the better your chance of winning. Well, with stats, the more tests you run, the higher your chance of finding a significant result that's actually just nothing, just random noise. Clearly, we need a better way. A single, powerful test that can look at all the groups at once without jacking up that error rate. And yep, you guessed it, that's where ANOVA comes in. All right, so let's get into it. What exactly is ANOVA? Well, the name itself, analysis of variation, actually gives us a really big hint about how this whole thing works. Basically, ANOVA is one single, powerful test that's built to check if there are any real, meaningful differences between the averages of 3 or more groups. It answers that first big, important question. Is there anything actually going on here worth paying attention to? And this is where the genius of ANOVA really shines. See, instead of comparing the group averages head-on, it takes this clever backdoor approach. It looks at variance, which is just a fancy word for how spread out your data is, and it breaks all that spread into 2 really important types. To really wrap your head around ANOVA, just imagine you're tuning an old radio. You're twisting that dial, trying to find a clear song. That's the signal. And you're trying to get rid of all that annoying static and hiss in the background. That's the noise. So, first up, ANOVA hunts for the signal. This is the difference, the variation between the groups you're studying. How far apart are their average scores? If the averages are miles apart, that's a really strong signal. Next, it measures the noise. This is just the natural, random spread of data you'd expect to see inside any one of those groups. Think of it like the background buzz, that static that's just always there. And this is the magic part. It all comes together in something called the F ratio, and it's literally just signal divided by noise. So if the difference between your groups is way bigger than the random noise within them, you get a big F ratio. And that's your clue that you've probably found something real, something significant. Okay, enough theory. Let's make this real. We're going to walk through a classic example using the most common type of ANOVA, the one-way ANOVA. So picture this. A researcher wants to know if 3 different varieties of wheat produce different amounts of crop. They plant a bunch of plots for each one, variety A, B, and C, and then they measure the yield. The big question is, are the differences in those average yields actually meaningful, or could it just be a fluke? Now, don't worry. We're not going to drag you through all the heavy-duty math. Here's the basic idea. First, ANOVA figures out the variation between the wheat groups. That's our signal. Then it figures out the natural variation within each wheat group. That's our noise. And then, you got it, it divides the signal by the noise to get that all-important F ratio. And, drumroll please, here's the final report card. The F ratio comes out to 1.5. And in this case, that number just isn't big enough to count as statistically significant. So what's the verdict? The signal just wasn't loud enough to cut through the noise. The differences in yield were probably just random chance, not because one wheat variety was truly better than the others. But, of course, the real world is usually more complicated than that, right? What if you're interested in more than just one thing? Like, what if you want to know about both the wheat variety and the type of fertilizer you're using? Well, that's exactly what two-way ANOVA is for. It's the next level up. It lets you test the effects of 2 different things at once, say, wheat variety and fertilizer type, on your final outcome, the crop yield.
Now, this is where it gets really, really cool. Two-way ANOVA can spot something called an interaction effect. This happens when your two factors don't just add their effects together, they actually influence each other in a surprising way. For instance, maybe fertilizer X is amazing for wheat A, but it's totally useless or even bad for wheat B. That's an interaction. It's the "it depends" effect. This chart right here is the perfect picture of an interaction. See how the lines aren't parallel? They actually cross. Look at that. Drug Y seems great for Group A, but for Group C, it has a negative effect. That crossover is the dead giveaway. It's a super important discovery that you would totally miss if you were just doing a simple one-way test.
All right, so let's bring it all home. We've gone through a lot here, so what are the key things you really need to remember from all this? Here's the bottom line. Anytime you find yourself needing to compare the averages of 3 or more groups, ANOVA is your best friend. It's the safe, statistically sound way to figure out if the differences you're seeing are the real deal or just random static. It's all about finding that signal in the noise. And that brings us to one last little puzzle to think about. See, ANOVA is kind of like a smoke detector. It's great at telling you that there's a fire somewhere in the building, but it doesn't tell you which room is on fire. So if our wheat test had found a significant difference, how would we figure out exactly which wheat variety was the best? Well, that's a story for another time.